Okay, now let's look at the spring mass systems and their most general differential equations, the non-homogeneous ones that have a forcing function on the right-hand side. So we have our differential equation, in this case non-homogeneous, y double prime plus c over m y prime plus k over my equals f of t over m, where f of t is the forcing function. Some function which is exerted on the spring but which is not a part of the spring. In some sense, this is just a non-homogeneous differential equation. Which can be solved by the method of undetermined coefficients. So in some sense there's no new material here, because if we just had numbers here and then a function for the right hand side, we'd use undetermined coefficients, and it wouldn't even matter that this was describing the motion of a spring. But there is a case that is interesting to look at, and so I want to analyze that case a little bit. In applications, f of t often has the form f of naught cosine of omega t for constants f naught and omega in the real numbers. And often damping is 0. So then we have y double prime no c plus k over m y equals f naught cosine of omega t. So then behavior depends upon whether omega is a root of the auxiliary equation or not. The auxiliary equation is r squared plus k over m equals 0. So the roots are plus and minus I square root of k over m. Let's define omega naught to be square root of k over m. Actually, when I said depends on whether omega is a root, I meant I omega, or omega I. So I'm saying we should check whether omega equals omega naught or not. If omega and omega naught are different, then the general solution to the differential equation the homogeneous differential equation y prime plus k over m y equals 0 is C1 cosine of omega naught t plus C2 sine of omega naught t. In a particular solution of the non-homogeneous differential equation, y double prime plus k over my equals f naught cosine of omega t is a cosine of omega t plus b sine of omega t. Now in this case, so our solution is a combination of cosines and sines with omega next to the t and cosines and sines with a different number, omega naught, next to the t. And solutions look maybe a little messy, so they go up and down, but not always the same height and not any fixed frequency or something. So you might think that's messy, but nothing, let's say, exciting happens. There are bigger vibrations and smaller vibrations, etc. Now, if omega equals omega naught, then in our particular solution we can't use cosine omega naught t and sine omega naught t, because those are already solutions of the homogeneous differential equation. We're going to need to multiply by a t, as we do when we see something that's already a root of the characteristic of the auxiliary equation, or a function that's already in the space of homogeneous solutions. So we have t times a cosine of omega naught t plus b sine of omega naught t. Again, cosine of omega naught t sine of omega naught t without the t's on the outside are already solutions of the homogeneous differential equation. So then the solutions to the non-homogeneous differential equation with an omega naught here, I'll write the equation down. Y double prime plus k over my equals f naught cosine omega naught t. These are the functions. So any linear combination of the solutions to the homogeneous differential equation, which are not those, but here we go. These. C1 cosine W naught t plus C2 sine of W naught t plus now t times these trig functions, t times a cosine W naught t plus b sine W naught t. Now this is a problem if we look at behavior as t approaches infinity. So these functions just go up and down between -1 and 1. Actually, negative c1 and positive c1. This goes back up and down between negative c2 and positive c2. But t times a function like this goes back and forth between t and negative t. Which means the vibrations get bigger and bigger and bigger without end. And this is how some machines end up exploding. Because the vibrations get bigger and bigger and bigger, stronger and stronger, until the machine parts just can't take it anymore, and the whole thing explodes. So for me, that's the most interesting phenomena that happens in the last section of the chapter on the differential equations with forcing functions. The end.